Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're fortunate enough to be joined by Ralph Lorenz, who's come across the country just for this talk, so we should feel honoured for that. Today he's going to talk to us about his favourite planetary body in Titan. Ralph started his education in the UK. He did a Bachelor of Engineering in Aerospace at the University of Southampton. Then he did a PhD in space sciences at the University of Kent, where he was involved in the design of the penetrometer for the Huygens mission, which travelled with Cassini, and I'm sure we're going to hear about today. After he finished his PhD, Ralph moved across the Atlantic and started work at LPL at University of Arizona. And just recently, in 2006, he's moved from Arizona to Maryland, and he's working at Johns Hopkins University Applied Physics Laboratory now. Ralph is a ultimate Frisbee enthusiast, and he's written a book on the subject, as well as several others, including a couple on Titan, Unveiling Titan and, Lifting Titan's Veil, and the topic of his talk today, which is Titan Unveiled. So if you'll join me in welcoming Ralph.
Thank you. Well, thank you, Adrian, and thank you all for coming. It's always a pleasure to talk about Titan. And thanks also to NASA's Outer Planets Colloquium series, which helped with the logistics of getting me here today. Always the challenge with a talk like this is to sort of, give something for everyone. I'm sure it's a very diverse audience. I will try, as usual, to hit a little bit on what's involved in implementing missions to the outer solar system, some of the experience of working on Cassini and Huygens. I'll talk about some of the things that I think are really cool about Titan, the dunes and the seas. Being as we're here at SETI at the Carl Sagan Center, I'll touch on astrobiology. I've also had a couple of special requests, one to address the prospects of cryovolcanism on Titan, which is intimately connected with prospects for astrobiology, and also to try and work in Australia somehow. I've got an hour to try and do that, so hold on to your hats. This, incidentally, is a beautiful picture of Titan in the background, taken by Cassini about a couple of years ago. This is one of the small moons, Epimetheus, maybe it's Pandora. So this picture is taken looking across Saturn's rings with Titan in the background. Cassini is just providing endless supplies of great pictures that are not just in the textbooks now, but even in the sort of coffee table literature. If any of what I talk about proves to be interesting, if you want to follow up, there's my website was on the first slide. If you Google me, I'm easy to find. Christophe Sautin and myself had an article that at least was very well illustrated by others, if not well written, in Scientific American earlier this year. That's fairly up to date. As was just mentioned, there are a couple of books, one of which has the title of this talk. In fact, the paperback edition of Titan Unveiled just came out just a few weeks ago, and actually has an updated chapter to sort of bring us up to speed from the 2008 edition. I venture that actually the first book, Lifting Titan's Veil, which was pre-Cassini, is still of interest. And one reason I didn't sort of just do a new edition is a lot of what we thought we knew about Titan has turned out to be wrong, often wrong for very interesting reasons. But science, of course, is a process. It's not an ultimate destination. So just having that record of why we thought what we did, I think is interesting and instructive. Getting on to the talk itself, the caveat I must offer is that this is just going to scratch the surface. There was a time back when I got involved in Cassini and Titan circa 1990 where you could sort of read just about everything that was known about Titan. You know, in the course of a few weeks, there was a few dozen papers, and there's always cross-referencings and duplications, but you could basically read everything that was written. That is no longer the case, driven largely by the data from the Cassini mission, but also still excellent stuff coming out of ground-based telescopes and theoretical and laboratory work. The Titan literature is now up at sort of 100 papers a year, so it's just hard to just read it all, let alone do any new original work of your own. Just to put Titan in context, here's a Hubble Space Telescope picture of Titan next to its parent planet. Titan is the second largest, only just the second largest satellite in the solar system. But it is, of course, completely unique among the satellites in that it has a thick atmosphere, an atmosphere predominantly of nitrogen, like our own, and in fact rather thicker than our own. It's more, I think, useful actually to compare Titan to the terrestrial planets than it is to compare it to other icy satellites. In some ways, mass-wise and radius-wise, it's not too different from Ganymede or Callisto, or even to some extent Europa. But many of the processes that shape the surface and the atmosphere, of course, are much more relevant to the terrestrial planets than to other icy satellites. Titan's atmosphere is thick and optically thick. Most of the sunlight gets absorbed high up, which is what happens at Venus. And both bodies are fairly slowly rotating in an inertial sense. And that slow rotation and optical thickness gives a sort of super rotating zonal wind system, which is more or less common to the two bodies. Titan's pole is inclined by about 26 degrees, much like the Earth and Mars, and so Titan has seasons, much like Earth and Mars, and volatile transports that are rather reminiscent of those bodies. And Titan has a hydrological cycle. In fact, Titan is to the Earth's hydrological cycle what Venus is to the Earth's greenhouse effect. It's a terrestrial process, terrestrial phenomenon, but taken to an extreme. Seems the rainfall on Titan, on average, is very low, but when it happens in very violent outbursts, punctuated by long droughts, which in a way is what you get if you take the terrestrial hydrological cycle and warm the atmosphere so that it sort of takes longer to charge up with moisture. So there's a lot to be learned by these interplanetary comparisons, and Titan's a really interesting object in that sort of parameter space. Titan takes 29.5 years to go around the Sun. Obviously, it's going around Saturn. It's actually tidally locked to Saturn, so it always shows the same face to Saturn, just as our moon does to the Earth. Christian Huygens, who discovered Titan in 1655 or so, remarked that the seasons on Titan would be sort of long and tedious because of this long year. It's worth pointing out also that Saturn's orbit around the Sun is not quite circular. It's appreciably elliptical, so it's about 10% closer near perihelion, which is near southern summer solstice, than at aphelion. And so there's a substantial modulation in the amount of sunlight just because of that changing distance. So that means that southern summer, at least at present, is shorter but more intense than the northern summer. That's also true for Mars for the same reason, that the orbit around the Sun isn't circular. And actually also for the Earth, the effect on the Earth is quite small. This 29-year timescale is actually kind of interesting because it's sort of rather commensurate with human careers. You can map out your life on Titan. I was born in '69, just before southern summer solstice. I went to grammar school in the UK, in England, and got a degree. Went to work for the European Space Agency. This is me with the project team just when the Cassini project started in 1990. Got a PhD, got married, came to the US. Then the Huygens mission actually happened out here. This is during the encounter. This is at the European Space Operations Center in Darmstadt in Germany. You can see the sort of chaos as the data were coming in. And just earlier this year, there was a sort of 5th anniversary of the Huygens descent celebration. This telescope at an observatory in Barcelona overlooking the city was actually the telescope that a Catalan astronomer in 1908, José Coma Sola, observed that Titan's disk, I mean, it's barely perceptible, it's just an arc second across, about the smallest thing you can see clearly through a telescope. He could tell that the edges of the disk were darkened, and he inferred that to mean that Titan had an atmosphere. So the whole story of Titan history, almost everything we know about Titan except for its discovery in 1655, has taken place over only 3 Titan years. So I urge you all to sort of make versions of this plot with your own sort of holiday snaps. But it is a very sort of human timescale. Note also, it was is 15 years from when Cassini was the Cassini project started in earnest. Money was really starting to be spent to when it actually happened. 15 years. So that's a timescale of which people have to remember how everything worked, and the documentation has to be tracked. There was, for example, reprogramming of some instruments that had to happen to fix a problem that was identified during cruise. And some of the compilers were no longer supported. People had to be brought out of retirement to do the fixes. This kind of knowledge retention issue is a real challenge for outer solar system exploration. It's really somewhat analogous to a crusade almost. You sort of sign up for a large part of your life to this kind of endeavor. Okay, so going back to northern spring equinox in 1980. That was when the sort of modern era really starts with Titan studies and the encounter of Voyager 1. And Carl Sagan was very active in studying Titan at this time. And if you're a planetary geologist, this was a very disappointing encounter. And actually Voyager 1 was targeted to fly close to Titan at the expense of any subsequent encounters with Uranus or Neptune. Because Titan was known to have an atmosphere, was known to be interesting, was known to have organics, and so that made it of astrobiological interest. And what was found was not much on the surface, because it turns out this thick atmosphere is laden with a sort of organic smog. Basically there's methane in the atmosphere that is broken down by sunlight, and the molecular fragments recombine to form a whole host of other compounds, a bunch of which were identified here in this Voyager infrared spectrum. So there's hydrogen cyanide, acetylene, ethane, ethylene, deuterated methane, HC3N, I always forget, is that acrylonitrile, acetonitride? Yeah, anyway, there's dozens of organic compounds. And really that atmospheric photochemistry was what focused Titan science at the time, because the geologists didn't have anything to work with. And really the dominant paradigm was one of methane in the atmosphere being broken down. It forms ethane, which is a liquid at Titan surface temperatures, and some other compounds, as you saw. And those would presumably accumulate on the surface. This cycle is irreversible, because the hydrogen that's released escapes to space and doesn't sort of restore the cycle. So it was thought that maybe there was a lot of methane at the beginning of Titan's history, and progressively that was converted into ethane. And maybe there would be enough ethane actually to completely cover Titan's surface, that it would be a global ocean of hydrocarbons. We didn't know any better at the time. So this is the sort of perspective that shaped the formulation of the Cassini mission, which was originally formulated in Europe in its ultimate form, but is actually formally an endeavor of NASA, ESA, the European Space Agency, which is how I got into this business, and the Italian Space Agency, which provided the high-gain antenna here. I'm going to be discussing a fair amount of geology in the rest of this talk, and just in the interest of full disclosure, I have never actually taken a geology class of any sort. I've sort of picked up a bit as I went along. My formal training is as an aerospace engineer, as you heard. But this is what makes planetary science and astrobiology so stimulating, that it's the intersection of many different fields of endeavor, and if you just restrict yourself to a narrow set of disciplines, you'll really miss out, because it's all interesting. Anyway, this is Cassini. This is about the size of a bus. It's the largest or most massive interplanetary spacecraft launched in the West. It's 2.5 tons dry. At launch it had about 4 tons of fuel on it, almost all of which has been used. It gets electrical power. Remember, we're 10 times further from the sun than is the Earth, so there's very little sunlight. It gets electrical power from these radioisotope thermoelectric generators. There's a set of cameras bolted to the side of the spacecraft. Actually, when Cassini was originally proposed, like the Voyager spacecraft, it had scan platforms articulated structures, so you could point the cameras in one direction and point the high gain antenna to the Earth. In 1992, there was a NASA budget crunch, as there often is, at the time involving the space station, and it's probably only the fact that Cassini was an international mission and the sort of shame that would result from pulling out that prevented its cancellation. But as part of the slimming down that had to take place to retain the mission, the scan platforms were deleted, which saves you money, gets you under the bar in fiscal year 1992, but actually pushes out a lot of extra operations costs into the present day. Because now all the different scientists, some of us, for example, working on the radar instrument that uses the high gain antenna, we want to point the high gain antenna at Titan, and the cameras are out pointing here. So every Titan flyby has to be choreographed like a Jackie Chan movie. You want to point the cameras here at this moment and then turn around to point the radar, but you've got to turn in such a way that you don't point the sensitive radiators of the thermal instrument at the sun while you do the turn, and all that has to be figured out in excruciating detail. Also hiding at the back here is the Huygens probe, which was the principal European contribution. Cassini is a model of international collaboration. There are contributions from Europe on many of the instruments on the orbiter, and there are contributions from the US to the main instruments on the Huygens probe were from the US. So there's sort of complete cross-fertilization, and there are in fact instruments that flew to Titan that probably are only on there as a result of this sort of broader solicitation of ideas. It's been very stimulating. I mean, different people work in different ways and come up with different ideas, and everyone is enriched as a result. I like to show this picture of the Huygens probe, not because I'm particularly fond of shiny gold thermal blanketing, but just to underscore why exploring space is difficult, why it takes money and effort to do all this. And the reason is that you might see a space probe here in a heat shield, but you've also got a structure that holds it up because somebody had to figure out that this back shell is going to have to attach to the front shell, and we have to hold it up in such a way that'll work. And then you have to have a facility, this is IABG in Germany, where the doors are big enough for this dolly to go through. There are dozens and dozens of boxes inside here, all of which have literally hundreds of electrical connections. Those all have to match up. The software in the camera experiment has to talk to the software on the spacecraft. And all those interfaces, the software, the human interfaces, the bolts, the electrical wires, all have to match up. And so there's this enormous coordination effort that has to take place, and that's why it's difficult. I'll point out this was all done, and this of course is nothing new in a way, but this was all done before the World Wide Web. We were doing this with faxed documents. There wasn't Adobe PDFs at the time. Microsoft Word hadn't established global hegemony at that point. The official word processor in ESA at the time was IBM's DisplayWrite 4. And I started out as a junior engineer in the ESA project team, and there's a 50-page fax coming through with an update to an experiment interface document, and it was yours truly that had to phone Aerospatiale in Cannes and say, can you send pages 23 and 27 again because they got smudged. That was how this is all done. Things are in a way a lot easier. Maybe it just means we just have to work harder and faster, but it's this coordination that is really the challenge. It's interesting that ESA has a way of working called juste retour, which makes pork barreling look like in some ways a little opaque, but in some ways easy. ESA has to allocate the contracts on its big projects in the same proportion that it receives budget from the member states. I mean, if you're a project manager in ESA and you just want to get something built and want it built so it'll work, just get the Germans to do the whole thing. You'll be fine. But what actually happens is to make the whole system work and get politically everyone behind it. You have to give kind of 25% to France and 20-some% to Germany and 15% to Britain. And you have to make sure that Belgium gets its 3% and Finland gets its 1.5%. So the technical solutions have to be modulated with this whole political story. So the parachutes on Huygens came from the UK. The software was done in the UK. The thermal design and the testing was done in Germany. The heat shield is made from French ballistic missile technology. The structure was built in Spain. The radar altimeters came from Finland. It all comes together in a really kind of opaque, kind of sausage-making way. But come together, it all did. And it took roughly 5 years, maybe a little bit more, for that whole project to get to the launch site. Obviously, the probe built in Europe had to be delivered to the US to be mated with the rest of Cassini at JPL before the whole stack was assembled at the launch pad in Florida. And it actually launched a couple of weeks late, but that was actually all to the good. Meanwhile, Titan was starting to get more and more interesting. In 1993, the Hubble Space Telescope was repaired, and that gave HST the capability to image Titan. And by looking instead of at the sort of orange wavelengths that the Voyager observed at, it was able to look in the near infrared, where Titan's haze is less thick and it's actually brighter. So it's like looking through thin fog instead of looking through thick smoke. And that imaging, Titan was only 18 pixels across, revealed this sort of leading edge bright area called Xanadu. Now we actually knew there was a leading edge bright area just by looking through ground-based telescopes at different times over Titan's 2-week orbital period. Because it's tidally locked, then over one orbit period it rotates under the telescope, if you like. And we saw in some near-infrared wavelengths that the leading face of Titan was appreciably brighter than the trailing side. This kind of light curve, this plot of brightness versus time or longitude, is probably about the best data we will get for some considerable period of time on extrasolar planets. In many ways, the study of Titan is kind of a prototype for extrasolar planet studies. So we knew that bits of Titan were brighter than others, which immediately begs the question, well, if Titan is being covered by stuff drizzling down from the atmosphere, why are some areas bright and some dark? What's keeping the muck from covering everything uniformly? That almost immediately suggests some sort of ongoing process, whether geological or meteorological or what. Okay, so Cassini was launched. Even on the largest launch vehicle in the US inventory, the Titan IV, that vehicle isn't large enough to hurl 5.5 tons straight to Saturn. We actually had to fly by Venus once, then Venus again, and then get an Earth flyby, and even a little boost from Jupiter. And even then, it takes 7 years to get out to Saturn. That time actually proved to be very important. We did a test. The Huygens probe, which parachuted down, would relay its data via the Cassini orbiter. So the signal would come up from Huygens, be received by Cassini, stored on board, and then Cassini would turn around and then send the data down to the Earth. We did a test during the Earth flyby with the Goldstone dish in Southern California, pretending to be Huygens. So it was sending a signal like Huygens, and then we'd use the receivers and stuff on Cassini to check that it was received okay. And in fact, it wasn't. That was obviously a bit of a surprise. And the immediate question is, well, did we do the test wrong? No, we didn't do the test wrong. There's a whole set of investigations, and we found, in fact, a design flaw in the radio receiver, which was built in Europe and bolted onto Cassini. But because we had this time, because we had 3 or 4 years to analyze the problem, understand the problem, and develop a workaround, we were able to fix it. Had we been going to Mars, or the Moon, and got there in 2 days or a month, it would have been much more of a challenge. So there's some lessons there about testing and buying radios from Italy, but the problem was identified and solved. Meanwhile, Titan continues to change. As I said, it had seasons. You may have noted on the Voyager picture, one hemisphere of Titan was slightly darker than the other. That's the difference in the amount of haze in the atmosphere. Actually, some of the haze gets blown from one hemisphere to another. And in fact, one of the best records of this is by a 21-inch telescope at Lowell Observatory in Flagstaff. Wes Lockwood has patiently just measured how bright is Titan at a couple of wavelengths over more than a Titan year. I mean, he's been doing this since 1970. And it shows, incidentally, that the cycle doesn't repeat. Titan is apparently changing from one year to the next. One of the contributors to this brightness is the Haze asymmetry, the one half of Titan being darker than the other, and that changes over the course of a year. But there's also this dark structure over the winter pole that seems to form as a result of that area being in winter shadow. And in many ways, there's some phenomenological similarities with the Earth's ozone hole. I mean, the chemistry is completely different, and the temperatures are different, and the length of the year is different, and so on. But fundamentally, you've got an area of stratospheric downwelling, bringing, in Titan's case, organic rich air, from where all this chemistry happens, down into the lower atmosphere where it can condense, where it wouldn't otherwise condense. There are compounds that would normally be destroyed by ultraviolet light that can build up during the winter because it's in shadow. And the whole area is sort of isolated from the rest of the atmosphere by a sort of circumpolar vortex, the polar winds. The same sort of thing happens on the Earth. You've got the circumantarctic current and the polar vortex that isolates polar stratospheric clouds, actually, of nitric acid that form in the Earth's stratosphere. And those cloud surfaces act as catalytic surfaces in the destruction of ozone. So again, the chemistry is different, but the physics is the same, and that's really a theme that recurs on Titan. So I better keep moving here. Also, during the early part of this decade, or last decade, telescopes, the large telescopes that were built in the late 90s, like the Keck, were able to start seeing cloud systems on Titan, clouds like we know them, methane clouds billowing up like cumulonimbus clouds, probably with rain and hail underneath them, clouds that evolve on just timescales of a few hours. And they're concentrated around the South Pole. Remember, this is during southern midsummer. So this is where the surface is being most strongly heated. So these are very much like the sort of summer afternoon clouds you get in the desert Southwest. As Cassini has been there, the cloud patterns have changed. In fact, we're starting to see more and more clouds in the north. That's probably a trend that will continue as we move into northern summer. So watch this space. Then Cassini arrived at Titan and has told us an enormous amount of things. One of the big surprises was just how rich the photochemistry was. This is a mass spectrum taken by Cassini as it flew through the upper reaches of the atmosphere. So this is at an altitude of 1,000 kilometers. If you did this experiment on the Earth, there'd be like 3 or 4 little peaks, oxygen and nitrogen, atomic forms, maybe some NO, something like that. But there's literally dozens of compounds here. It was a surprise that things even as high as benzene and toluene, mass is 72 and higher up. The instrument only went to 100. So the chemistry is very, very rich, even well above the surface. Both ion chemistry and neutral chemistry, for that matter. And in fact, there's some less direct ways of measuring that there are compounds with atomic mass of thousands, literally thousands, forming up there. So it's a very rich chemical factory. But from an astrobiological point of view, even though there's all these organics and compounds including nitrogen in them, so nitriles and others, there's very little oxygen in Titan's atmosphere because it's so cold. The vapor pressure of oxygen-bearing molecules is very low. There's a few parts per billion, I think, of water vapor. There's some CO. There's a few parts per million or billion of CO2, but they're really traces, much as, say, CFCs are traces in the Earth's atmosphere. And biological molecules have oxygen in them. Sugars and amino acids all have oxygen. So that synthesis can't go all the way to living things or whatever in the atmosphere alone. But that's not where the story may stop. In fact, Carl Sagan back in 1990 was really the first to point this out, that while you can have this photochemistry that gives you what he called tholins, after the Greek word for mud, oligomers and polymers of hydrogen, carbon and nitrogen, that stuff will accumulate on the surface. And if it gets exposed to water, liquid water, then laboratory experiments done among us elsewhere at Ames show you very quickly synthesize things like amino acids and pyrimidines, which are one of the bases that encodes information in DNA. You form this stuff in hours, but geological structures where you might have liquid water, as for example from a cryovolcano or from an impact melt sheet, those structures will last for thousands or tens of thousands of years. And that's not an experiment you can really do in the lab, at least not with current NASA funding cycles. So we don't know how far down the chain of complexity that ultimately leads towards living things this kind of chemistry has occurred on Titan. There may be functional systems like autocatalysis, information storage, duplication that can happen in this sort of environment before it freezes. That they may occur deep in Titan's interior, which we think is liquid, but we just don't know until we kind of sample this material directly. There's even the prospect, admittedly a distant one, that this kind of chemistry might be able to occur in a non-polar solvent, and Titan has these lakes and seas of liquid hydrocarbons, but that's recognized as speculative, but one can never say never. So this is the framework for a lot of the astrobiological interest on Titan, is just how far down the chain of complexity has the chemistry gone there. And that's prompted a lot of debate, in particular because of this notion that if liquid water is erupting from Titan's interior, as the cryogenic equivalent of a volcano, then there's all this interesting prebiotic synthesis. That makes Titan a very interesting place to visit. And there was in the last few years, there was a sort of choice NASA had to make between going to Europa first versus going to Titan first. And I think this debate about cryovolcanism figured into that. This is a Cassini near-infrared map showing Titan's surface. There are dark areas, which I'll come back to, and bright areas. And there are some areas that are distinct in composition. The red color in this plot is at 5 microns. There's a couple of particularly bright 5-micron areas. And these, when you look at them more closely, seem to have, and the evidence isn't great, the resolution is not what we'd like, they seem to have kind of lobate flows, which are often associated with volcanic processes. And that's been suggested as evidence for cryovolcanism on Titan, so just the areas where this interesting prebiotic synthesis might take place. There have been some Europa people, if I can characterize them that way, that have contended that the evidence for this is not great, and they're right. The evidence so far has not been terribly persuasive, but the debate's going on, more data is coming in, and negatives are very hard to maintain in the face of more and more data. This is a radar image. This is about 100 kilometers across of that red bright region, Hote Regio. And these sort of, again, lobate morphologies are very similar to those that are seen in radar images of volcanic flows on the Earth. So this is certainly a possibility. It's been argued, and I think Jeff Moore gave a talk here some months ago arguing that you can get lobate morphologies from landslides, for example, or maybe fluvial deposits, and that's true. That needs to be looked at. I think there needs to be a more systematic, maybe quantitative evaluation of morphology, because morphology is always one of these squirrely kind of disciplines where some people could say, oh, it looks like a frog, and other people say, no, it looks like a whale, and you kind of can't really argue it. This area had been claimed to show photometric variability. It was like brighter at some times than others, and it had been suggested that maybe this was some sort of eruptive process. That data has been disputed by members of the same team, actually, so I'm not sure that evidence is terribly strong. There is more and more topography data coming out of Cassini from principally the radar instrument, both stereo and another technique, showing that some of the structures advocated to be cryovolcanoes are maybe not as persuasive as they once were, but there are others maybe that are looking quite compelling. So stay tuned. The debate is still ongoing, as it should be. That's what science is all about. The paradigm has been articulated that Titan doesn't have cryovolcanism, doesn't have tectonics, it's dead. There is, I think, relatively undisputed evidence of tectonic deformations now. There's these mountain sets that seem to appear in sort of ridges of sets of 3 for some reason, but they look very much like tilted blocks. Many of these areas on that leading edge bright area, Xanadu, have a sort of rectilinear pattern, and in fact there's river channels in them that similarly have a rectilinear pattern that suggests tectonic control. Many of the mountains appear in these sort of belts in this sort of chevron pattern. near Titan's equator. Getting straight lines, getting chevron patterns might be indicative of tectonics. I don't know how else to make mountains this way. Again, it's an ongoing debate, but there's more and more data coming in. So just to summarize this debate, since it was sought specifically, I don't think there's ironclad evidence of present-day volcanism. I mean, this photometric variability is not a strong constraint. There have been suggestions that some of Titan's clouds seem to appear in some places more than others, and in fact, meteorologically, the atmosphere is rather dry to expect clouds in the low latitudes. So maybe there's some sort of methane venting. The presence of argon-40, the radiogenic isotope of argon, in Titan's atmosphere does require that this stuff has been brought to Titan's atmosphere from the interior, because it's released from potassium, which is in Titan's interior. And there's no reason Titan shouldn't have cryovolcanism. If you just express the 10% of the geothermal heat flow we'd expect as the latent heat of water magma, you get many cubic kilometers per year. It's perfectly viable. And in fact, the ammonia that may act as a sort of antifreeze in Titan's interior makes cryomagmas more buoyant than they would be with pure water. And this doesn't, it's irrelevant how thick the ice is above this process, above this layer. There are ways of getting liquids to the surface. The morphological evidence is not evidently persuasive, at least not completely persuasive on an individual basis, but there are enough different places on Titan that look like they could be, that it's hard to argue that none of them are. And what I find is a particularly compelling issue is the spatial coincidence. The fact that areas where we see in different data sets stuff that looks like flows are the same areas that have a distinct composition. That almost suggests to me that something has come out from the inside. It's not just eroded down from the hills. But whether that's cryolava in the sort of sense people think of as water erupting from the interior is another story. Jeff Cargill has advocated, keeping an open mind on all the different organics there could be. In Arthur C. Clarke's 1970s science fiction novel set on Titan, which I particularly like because it had Scots as the protagonists. He was actually inspired by the latest information from Carl Sagan, but he about Titan, not Scots. He talks about waxworms, this kind of exotic landform that sort of has stuff hosing out from the interior and then congealing in Titan's surface. Maybe we need to think about something like that. And as a sort of cautionary example, and I repeat, I'm not a geologist, I like this. Is this a lava flow, or is it a fluvial feature or a landslide feature? I mean, it sort of looks low bait to me. You show of hands for lava? 2, 3, 4, not many. Show of hands for fluvial? 1, 2, 3. Okay. Well, it's if you speak Farsi, then you'll know this means mountain of salt. This is actually a salt glacier. This area is in southern Iran. It's heavily tectonized. There's a huge layer of salt formed in the Tethys Sea when it evaporated hundreds of millions of years ago. The salt is being squeezed tectonically and actually hoses out of the ground and flows like a glacier. It doesn't flow very fast. Salt is kind of a rock, but it's actually a very soft rock, so it does flow. But if this were on Titan and we were classifying it, we might say it's a lava flow, but it's not a lava flow. So is there something like that on Titan that is fooling us? Don't know. I think we need to keep an open mind. Okay, I need to press on. Huygens was released on Christmas Eve, actually, 2004. We actually, on Cassini, felt the reaction as the springs pushed Huygens away on some spiral rails to give it spin stabilization. We can see that reaction here. We actually caught pictures of it as it sailed off in the distance. This is from 52 kilometers away, about a day after release. Really amazing picture. I'll point out that a year before this, a picture like that, but actually a rather better picture, was the last that was ever seen of the Beagle 2 spacecraft. So people were nervous. But Huygens entered. It was largely successful, barring another radio problem. There was an interesting anomaly with the parachute descent in that there are these little winglets on the side of the probe that were supposed to spin the probe in a known way. during the descent to pan the camera around. The camera's looking down and outwards to the side. And in fact, we think we understand why now, but it turned out it spun the wrong way, which meant the camera data took a lot longer to analyze. I mean, the data was still acquired fine, but it took longer to analyze than it would have done. But just to make the commercial break, that story is discussed in my book, Spinning Flight, and there's another book on space systems failures more generally, all available at your favorite online or real-world bookstore. Anyway, the Huygens probe landed. We had no right to get this picture. We had no right to expect to get this picture. The Huygens probe was designed when we didn't know anything about the surface of Titan. We didn't know if we were going to land in a global ocean of liquid hydrocarbons. We didn't know if we were going to land on a solid sheet of ice or a big pile of foo-foo dust that we just float through. Didn't know. We made sure the probe would have enough battery energy to last for 3 minutes after the longest possible descent. We made sure the communication link would be open. We made sure it would be warm enough. As it turns out, it landed on this outwash plate. I mean, these are rounded cobbles that have been tumbled in a methane stream. And this picture is taken from about knee high, just out for perspective. It could have been that the parachute would have fallen on the camera. Didn't happen, happily. We got this picture. We got like 100 of these pictures. In one of those pictures, there's kind of a blob in one corner that Eric Karkoschka is modeled as a methane dewdrop, basically dripping off the camera baffle. So the surface was warmed a little bit by the probe, and in fact the heated inlet of a gas analyzer that was on the bottom of the probe. And that heated inlet volatilized some of the surface material and showed what might be benzene, CO2, ethane. The ground was in fact, seems to have been actually slightly damp. And that's where my favorite 14 grams of the 200 kilogram Huygens probe comes in. As a graduate student in the UK, I got to specify, design, build, and test this thing called a penetrometer. It's literally the size of my finger, 14 millimeters in diameter. It's a disc of a piezoelectric ceramic, so a disc material that generates a charge when it's squeezed. So just like a igniter for a gas fire, you squeeze it, it makes a charge. So this thing is sticking out of the bottom of the probe, and if the probe is landing in sort of nearly vertical orientation, this thing gets rammed into the ground and records a force profile. And that's what happened. And during my PhD, I tried it in dry sand, and dry sand has this nice convex profile. When you squeeze dry sand, the grains sort of lock up, so you get this increasing resistance with depth, very characteristic of that kind of material. Wet clay deforms as a sort of plastic, has a constant resistance, and gravels have a spiky signature with the size and spacing of the spikes relating to the particle size. All made sense to me. Then we got the data from Titan, and it looks like none of these, which is great. That's the way science is supposed to work. And we had to make sense of this, in this crowded room at about 9 p.m. on a Friday evening, with the media watching closely. I mean, there were about 80 scientists from the Huygens teams at Darmstadt, and about 200 journalists. It was literally a siege mentality. Anyway, we had to get results for a, was it 11 p.m. press briefing, something crazy like that. And we hadn't seen the pictures at this point, right? We were just interpreting the little squiggles we had from our instrument. And so we thought, well, okay, this is, I spent about 3 years designing and building this as a graduate student. Then it went in a closet, got bolted onto the spacecraft, got broke by a technician. It's actually the flight spare that went to Titan. So 7 years later, a billion miles from Earth, 200 degrees Celsius below zero, it worked for the 1/20th of a second that it was supposed to work. So I was very pleased because my bit hadn't croaked. So this bump actually is the back end of the mounting stalk hitting the ground. So we can sort of dismiss that. Then it looks kind of flat, a bit like the wet clay, right? And this resistance is actually fairly weak. So you could get something like packed snow, or wet clay would have that sort of resistance, maybe wet sand. And then there was this spike at the beginning. What was that spike? Could it have been like a spark had jumped from Titan's surface just when the probe arrived, or was there a crust on top? We thought, kind of wet clay with a crust, kind of like creme brulee. And we sort of put that on the view graph. And our boss, John Zarnecki, the principal investigator of the experiment, actually used that in the he hesitantly used it in the press conference, and the media loved that. Food analogies go really well, apparently. The headline in Nature magazine was, "Titan team gets its just desserts from creme brulee surface." Though we actually don't think now that it was creme brulee after all, that actually the instrument may have hit one of these cobbles, and that's what gave the spike. But anyway, that was all jolly good fun. At the bottom is the moment of impact, 8869.7598 seconds. That was actually a very important number within our team because we had a sweepstake running on the duration of descent. There was actually something like a 15-minute, plus minus 15-minute uncertainty in how long the descent would take, because you never know quite the drag coefficient of the parachute. We had uncertainties about the atmosphere. We didn't know the topography of Titan. Would we land in a valley? Would we land at the top of a mountain? So there's half an hour of uncertainty, and we were actually right at the edge of that uncertainty band. But John Zarnecki, the PI of the surface science package, actually won the sweepstake, which was this bottle of Lagavulin single malt you can see in the foreground. I guess that's why they put him in charge. So one thing that wasn't noted, everyone really focused on the fluvial channels in the foreground here in this mosaic. The Huygens probe landed about here. This bright triangle is about 7 kilometers across, and there are all these nice river channels that showed immediately Titan shaped by hydrologic processes. Off in the background, there's these dark stripes, and we didn't really pay much attention to those at first. When the area was observed by radar not too long thereafter, summer 2005, we got the sense of what those really were. This is a radar image about 200 kilometers across, and these are sand dunes, not made of sand, but made of something else. And they're huge. They're tens to hundreds of kilometers long. They're about 1 kilometer wide. Analysis shows that in some cases they're about 150 meters high, and they more or less cover the equatorial regions. Morphologically, and I didn't recognize this at the time, they are very like these linear sand dunes seen in the Namib Sand Sea, and there's a nice quote by astronaut Musgrave here as he saw them from the space shuttle. This is actually a handheld digital camera picture out of the window of the space shuttle. But these are about the biggest dunes on the Earth, but they're same size, same morphology, and really compelling analogs for Titan. It's a kind of dune that actually forms in a wind regime that flips between 2 dominant directions, which is unusual in the Americas, which is why we don't have many of that kind of dune here. I won't go into that. There are some nice analogs. I'll see if anyone can guess where this is. But looked at from the air out of the airplane window, there's some hills here, and you can see the dunes sort of diverting around. This kind of linear dune that forms in this bidirectional wind regime. The dunes sort of line up along the sort of vector mean wind direction, and it's interesting to see how they sort of deviate around or break through these topographic obstacles. So if you haven't figured out where they are, maybe this picture will tell you. This is Jenny Radebow, a collaborator who works with me a lot on these dunes. You might be able to see some animal tracks here, a set of 2 prints with a sort of tail dragging between. It's either a velociraptor or a kangaroo. These are dunes in the Simpson Desert, about 50 kilometers southwest of Alice Springs in Australia. But as I say, understanding how these dunes interact with the topographic obstacles is really helping us understand what we're seeing when we look at Titan, because we see this same sort of process. This bright area here is elevated, we think, and the dunes are sort of deviating around it. And when we do that analysis, and Janie has mapped out something like 16,000 individual dunes, and they cover all the dark areas around Titan's equator, and you can see them going around this crater ejector blanket here. They all point in this direction. They all go from west to east. And that's interesting because all the modelers who build numerical models of Titan's winds say the wind should go the exact opposite direction. And that's the great tragedy of science, a beautiful theory destroyed by an ugly fact. But it's saying that saying there's something in the models, something that needs to be in the models, perhaps, that is on Titan. Titan is telling us something here. And in fact, this debate may have just been resolved. Actually, I had a commentary piece published just last week in Science magazine reporting on the work of Tetsuya Takano, a very prolific modeler in Germany. who indeed finds, as everyone else has found, that the low latitude, low altitude winds should be predominantly from east to west, i.e. opposite to where the dunes go. But for a brief period during spring equinox, or fall equinox for that matter, there's more mixing as the intertropical convergence zone crosses the equator. And the winds there actually, for a brief period, exceed the sort of average winds blowing in the other way. So if the sand only responds to winds of, say, more than a meter a second, then it's only going to see those eastward winds during that brief period. So it's only by looking at the statistics of the winds and the rare but stronger winds that blow towards the east that you can explain what we see. So that's been reassuring because that was kind of a big puzzle for a while. Moving away from the equator and to the poles are really the most fun part of Titan, namely the lakes. This is again a radar image about 200 kilometers across. We see lakes of all shapes and sizes. These kind seem to be seated in pits several hundred meters deep, a few tens of kilometers across, often kind of more or less equant, more or less sort of circular in plan form, although irregular. They look a lot like dissolution features, where the liquid is etched into the surface, which should be kind of hard to understand. What we know about the solubility of ice is in liquid hydrocarbons. There are other areas where there are, in fact, much larger seas. This one, Ligeia Mare, is several hundred kilometers across, that look like what are called Ria coastlines, where the liquid level is risen and sort of flooded valleys. So it may be that there's change in either the amount or the distribution of liquid on the surface. And one's reminded here of Lake Mead, which has the same sort of irregular outline because the liquid level has risen because we built a dam there. I'm not a geologist, but I occasionally play one on TV. This is from a film shoot for a Discovery Channel thing last year. This is me in a helicopter over Lake Mead. You can see, in fact, the door is open in true Apocalypse Now style. I think this stripe is something to do with the way the readout of the camera works with the chopping of the sunlight by the rotor blades. But I'm sort of gesticulating about how cool Lake Mead is and how much it looks like Titan, specifically the irregular flooded coastline, which suggests that geologically the liquid level has risen. But you can also see this sort of bathtub ring, this white layer, where in recent years the liquid level has dropped because of the drought. And actually that same thing has been seen elsewhere on Titan. There's a lake in Titan's southern hemisphere called Larcus, Ontario, which seems to have a sort of bathtub ring as well, suggesting it may have dried out. More recently, we've observed that with radar, and work by Alex Haze and others has found first that there's an altimetric profile across the lake that shows indeed the lake is flat, as we'd expect, and the margins are very shallow. The slopes here are very, very gentle. In fact, rather similar to slopes we see at a morphologically similar feature on Earth. This is Racetrack Playa in Death Valley National Park. And in fact, the margins of Ontario seem to have shrunk. Sorry, this is about 200 kilometers across, so it's about 50 times bigger than Racetrack. But you can see the shape is rather similar, perhaps for similar reasons. There's things that look like they might be sort of deltaic deposits here. They connect to river channels. But the shoreline seems to have receded actually in the 2 or 3 years that Cassini's been observing, suggesting that Ontario may be drying out. And Alex Haze has mapped this shoreline recession, and the fact that the edge of the lake doesn't get totally radar dark just at the edge, but it kind of fades off. And if you look at the fading, it's exponential, as you might expect if the slope and the texture of the lake bed were the same on the dry side as on the wet side, and you're just looking through an ever-increasing column of liquid. And you can go to Gaz de France, as one of our collaborators did, and pour out some liquefied petroleum gas, which is chemically the same as what's in this lake, liquid ethane and methane, and measure its microwave absorptivity, and the story hangs together. And it looks like Ontario, Larcus, has dried out by about a meter or two a year over the last few years. So it's a dynamic place. Just out of interest, you can see Racetrack Playa off in the distance. Took this picture from the airplane yesterday. Racetrack is very flat, and for 350 plus days a year is bone dry, but occasionally it does flood, and there's the whole story of the moving rocks I won't go into. It's dead flat. It can act as a perfect mirror, as you see here, even though it's outdoors, in fact will dry out in the course of just a few days. So it's a very dynamic environment. Ontario on Titan seems to be dynamic similarly, but it's on Titan things are a little bit slower. But it's a good model. And this is really a theme I want to reinforce, is that we can really learn a lot about what we're seeing on Titan by looking at places on the Earth. It's not only educational, it's also kind of fun. One of the big surprises actually with Titan is that the distribution of lakes in the north, polar regions in the south, is quite different. There's all these large seas like Ligeia here and Kraken in the north, and there's just one very shallow and drying out lake, Ontario, in the south. We don't think that's a seasonal effect because there's just so much liquid in here. I mean, about 100 times all the liquefied natural gas and oil that we have on the Earth, we think is found in these northern lakes. There's no way you can perform a seasonal transport of all that volume of stuff on Titan if we understand the meteorology correct. I mean, it's just basic energetics. There's not enough sunlight to do it. But maybe there's something happening longer term, and one is reminded here of the difference between the north and south poles of Mars, which have very different polar caps, both in extent and composition. And that's forced by in part by topography and in part by the seasonal asymmetry, that the southern summer is shorter but more intense than the north. And Oded Aronson at Caltech has pointed out that this arrangement of the seasons on Titan would change over astronomical timescales, just as the changing orbit of the Earth gives us the Milankovitch or Kroll-Milankovitch cycles that force the ice ages, and similar cycles occur on Mars. So on Titan, the polar insulation varies on timescales of tens of thousands of years, and that is enough, perhaps, to transport the liquids around. So we're seeing this very terrestrial kind of phenomenon. One puzzle, an outstanding puzzle about the lakes is, so far they seem to be dead flat. This is a plot actually by Lauren Y, who's here today from Stanford. This is a histogram of the amplitude of echoes from down-looking altimeter pulses. And over land surfaces where you've got lots of different facets on lots of different places, you get basically a Gaussian distribution, because you're kind of randomly adding lots of little echoes together. But the lakes don't look like that. They have this very odd sort of saddle-shaped distribution. Basically, if you're on a swing, you spend more times at the end. So it is with sampling the little sinusoidal chirp from the altimeter. And that's basically showing that the lake surface is acting like a point source, or even a perfect mirror of the radar. It's like pointing this laser altimeter at the ground. This shows the lakes or Ontario, at least on this day, was dead flat. And in fact, Lauren put an upper limit of 3 millimeters on the surface roughness. So that observation isn't unique in the sense that last year there was an observation in the near infrared by the VIMS instrument of the sun glinting off the surface of what's actually Jingpo Lacus, Mirror Lake, near Kraken. So the northern hemisphere lakes, at least on this one occasion, are also dead smooth. And that's a bit of a puzzle. I did some experiments across the street at Ames a few years ago in this Mars wind tunnel, which is this extraordinary building. Basically, it's this huge former rocket testing facility where you can close the big door and pump all the air out. I mean, it's quite absurd. But there's a little wind tunnel in it which is used for studies of Martian sand dunes and things like that. And we put a tray of water in there and pumped the air out and ran the wind at different speeds, just to see how easy is it to make waves in thin atmospheres, because it's believed that Mars once had seas, at least transient seas. So why aren't there more wave-cut beaches? Wave generation has been throughout history an empirical science. The mathematics is very, very challenging. So the easiest thing to do is set up some buoys and measure the wind speed and measure how big the waves are, get a big cloud of points and put a line through. Well, that doesn't work if you're trying to predict what the wind speeds need to be on Titan for making waves, because the gravity is different, the liquid is different, the air is different. So you've got to somehow generate a more fundamental understanding of this very important process. So we made some waves at different speeds in this tray. We colored the water blue just to make it nice and easy to spot. This is Erin Crail, who was a geology graduate student at UC Santa Cruz, who helped me with this. And in an idle moment, we also went and got some kerosene to kind of simulate Titan stuff. And we found that for a given wind speed, you get bigger waves in kerosene than you do in water. Not an experiment anyone had bothered to do it up to this point. Now, the viscosity of kerosene is different from water, the density is different, and the surface tension is different. So which of those factors matters most, we don't know yet. But notionally, hydrocarbons look like they should be easier to make waves in. So why don't we see waves on Titan yet? Well, one possibility is that the stuff precipitating out of the atmosphere isn't pure ethane and isn't pure methane, but there's propane and hydrogen cyanide, and these things are all more viscous when dissolved in hydrocarbons. So maybe the lake is kind of tarry. Maybe that's why we're not seeing waves. And there's this nice art exhibit in London, which is actually made with steel and used sump oil. But you can see you can make a very good mirror out of tar or oil. Maybe Titan's lakes are like that. The other possibility is that we just haven't been looking on windy days. This is a plot of Titan's year, 0 to 360 is a kind of standard measure of seasonal change. Cassini's observations have been, since it arrives in 2004, have been out here and out here, during which time this model by Tectonics shows that the winds, at least near here at Ligeia, have been quite gentle, probably less than the threshold required to make waves. But in the next few years, the winds will pick up and maybe we'll see waves in action. That brings me to mention a proposal I've been busy working on with others for a future mission to Titan, a discovery mission to parachute a probe with a nuclear power source into Ligeia Mare, so where it would float, would analyze the composition of the liquid, measure the waves, measure the winds, image the shoreline perhaps, because now we know where the liquids are. The Huygens probe was designed with this sort of scenario in mind, but landed in the equatorial deserts because we didn't know there were equatorial deserts at the time. Of course, this isn't the only thing one can imagine doing. Aeroplanes have been proposed for Titan, rovers, helicopters, landers, even hovercraft. In particular, hot air balloons. In Titan's thick, cold atmosphere, hot air balloons work very well. There's almost no vehicle that one can't imagine viably working on Titan. I mean, it's a wonderful place to explore. There's a lot of possibilities. Who knows what will happen in Europe with NASA with regard to future programs. As I say, there's proposals in work for some. Some of these are probably ideas that are still a couple of decades away. But whatever happens, Cassini is still orbiting Saturn. It's still flying by Titan every few weeks. There were 44 Titan flybys in the 4-year nominal mission. Cassini held up well. Its fuel supplies are lasting. The radioisotope power, of course, continues to work. So we had a 2-year extended mission with another 20-some flybys. And NASA has approved, pending continuing good results and performance of the spacecraft, an extended mission, the solstice mission, through to the summer solstice. So we'll really see the seasonal change happening in the north as the sun illuminates more and more of these large seas. So another, 50-some Titan flybys over 7 years. There's a lot to look forward to, and more flybys of Enceladus and pictures of the rings and everything else. So there's a lot to look forward to. Let me close with the remark that some people have argued on the use of the words Earth-like to describe Titan. And whatever the difference is, I've argued there are similarities. There are enough similarities that, at least for me, it's been very useful to study the Earth to see, to try and understand what's going on at Titan. So from a utilitarian perspective, there's a lot of interesting analogies. So let me stop there and take questions. Thank you.
Rolf, could I get the first question in? The Xanadu's brighter albedo in the near infrared, what's thought to be causing that at the current time?
Yeah, that's a long and disappointing story. one of the challenges of trying to understand composition on Titan is that because of the thick atmosphere that's laden with methane, methane absorbs light in broad bands. So there's only little bits of the spectrum that are accessible. And the spectrum in those windows is at least open to enough interpretations that there hasn't really been a unique determination of what that is. That might be generic to spectroscopists as a whole, regardless as to whether there's only little bits of the spectrum available. I can't comment on that. We do know that the material is bright at several wavelengths. There's also radar data that suggests that Xanadu depolarizes radar echoes. So it has some sort of funny texture to it. We know on a macroscopic scale it's rough. It's very mountainous and rugged. It turns out it's not actually elevated, which is what everyone thought before Cassini arrived. But the radar topography shows that actually the whole area is actually somewhat depressed. Now, the mountains may poke up above the base level. So something has been going on there, but we don't know what it is. It doesn't appear to be pure water ice. That much, I think, is agreed upon. There is a spectral signature that has been attributed to water ice in areas near the bright areas like Xanadu that suggests that maybe where you have fluvial erosion transporting material, that somehow cleans some stuff off and exposes some water ice, and that maybe the strongest water ice signature is actually in a crater ejector blanket. So, we're confronting very much kind of Martian issues of, what's the dust or whatever crud that's covering everything, and what's beneath. But of course, the amount of data we have is very much less. So I'm afraid I don't have a good answer for you. Probably organic, but we don't know.
Hi, Ralph. Thanks for a great talk. There was a commotion that I know you're familiar with a couple of months ago, maybe it's a little bit more than that, when a couple of papers were overinterpreted by the media as indicating that maybe life had been discovered on Titan. Could you tell us what those two papers actually were about and how you're interpreting the results?
Right. It's like dinosaurs and astronomy, right? There's a couple of things that everyone wants to be the one to discover or predict, which is volcanism or life. In this case, the debate, which I think even was prompted by a press release rather than an actual new scientific work, in the spirit of organic processes in exotic media, Chris McKay here at Ames had published a paper maybe 2005, several years ago, just pointing out that acetylene on Titan is potentially a viable energy source, and if it were being used by a biological system or some other chemical process, then that would lead, I think, to a depletion of hydrogen, molecular hydrogen. There had been an analysis of the measurements by the Huygens probe of molecular hydrogen in the atmosphere. And I think when people have tried to fit those measurements with models, one little fudge you put in the computer program to make the data go through the curve go through the points was if you have a sink at the surface. So, somebody put 2 and 2 together and said, oh, there's a sink at the surface. This paper says, well, if there's life, it would use up hydrogen, therefore life on Titan. So I think that's kind of the thought process. If you look at each of the steps in that, you run into some big questions like, well, how good really are those hydrogen measurements? How significant is the insertion of a sink term to make the fit better? And, well, okay, if you have hydrogen and acetylene, how viable is it really to have some sort of chemical process that uses it up to yield energy? So that's the background. Storm in a teacup. I really don't think we have the extraordinary evidence that Carl Sagan would require for an extraordinary claim.
What is the temperature and pressure, or nominally the temperatures and pressures on the surface?
I really should have started out with that, shouldn't I? I do apologize. The surface pressure at sea level, and we can actually use that word, is 1.5 bar, 1.497 bar, I think, at the Huygens Landing site. The temperature of the atmosphere at the Huygens Landing site was 93.6 Kelvin. We are pretty sure that the poles are about 2 Kelvin, 3 Kelvin cooler than that. Maybe during the peak of summer they get a couple of Kelvin warmer than that. The gravity on Titan is about the same as the Earth's moon, 1/7 of the Earth, or 1.3 meters per second squared. So to get that 1.5 bar, which is just after all the weight of the column of air, you actually have to have 10 times that column. So Titan's atmosphere is very, very broadly extended into space. I mean, the Huygens probe threw out its parachute at an altitude of about 160 kilometers, which on Earth is kind of in orbit. The density of the air at sea level, and the air is 95% nitrogen and about 5% methane. The methane humidity may vary a little bit, much as the water humidity varies on the Earth. But the density of that air, because of the low temperature, is about 4 times that on Earth. So it's a very easy place to fly in any means. And Bob Zubrin once calculated that a human being could strap wings onto their arms and flap and take off. That wouldn't be very clever. The thing to do would be have a sort of bicycle kind of thing, like a gossamer albatross or whatever. But heavier than air aviation works very well, and actually there's a proposal that NASA Ames here is involved in for a Titan aeroplane in the upcoming Discovery round. As I say, because the atmosphere is very cold, a hot air balloon actually works very well. And one reason that's been advocated is that you could use the waste heat from the radioisotope generator that you'd need to take anyway to have electrical power, but the waste heat is enough to keep that thing warm. Of course, just like many of these other sort of empirical things I've talked about on Titan, hot air ballooning has a long enough history that it's very empirical. People just know, because they do what everyone else has done for 50 years, that 2 tanks of propane is about good for an hour. But the actual fundamental calculation of how much mass can you carry in a hot air balloon of a given size with a given amount of heat, there's no formula for that. I had to work one out a couple of years ago because we were doing these mission studies. But it's really fun, and it's very much a recurring theme in Titan studies is to be confronting these sort of empirical things and have to look at them anew and understand them in a more fundamental level. Both wind wave generation and hot air balloons and all these other things. It's a really, really kind of fun amusement park of science.
Well, just one comment, if anyone's looking for life there, at 90 K the reactions are going to be pretty slow, and it's hard to imagine that much metabolic stuff could go on.
Absolutely, and that's why these transient environments like cryovolcanoes are of particular interest. I mean, if you were doing the same sort of study on the Earth, you would say, oh well, the Earth's surface is too cold for molten rock, and it is, usually. But that doesn't mean you can't form minerals hydrothermally. You can't get big, thick bands of nickel like in the Sudbury impact structure in Canada. So you're right, Titan's surface is too cold for metabolic processes of any sort to take place quickly. Whether there are environments at or near Titan's surface that can allow things to happen very slowly, that still needs some laboratory work that probably is going to be really challenging. But you're right. One of the reasons Titan is interesting from this sort of pre-Bartic synthesis point of view is that unlike the Earth, not everything has been digested and modified. This pre-Bartic synthesis has been frozen and the stuff is sitting there for us to analyze. I think Titan is very much more a body where we can understand origins of life processes than it is a place where we are likely to find extant life.
Do we know the thermal gradient as we go down the subsurface of Titan?
We can only estimate it, we know how massive Titan is, and so we think we know that it's roughly half rock and half ice. And from the amount of rock, assuming it's chondritic rock like meteorites, then we know how much radiogenic heat is being output. It's probably not much tidal heating, maybe about as much as there is radiogenic. So that all amounts to 5 or 10 milliwatts per square meter of geothermal heat flow. On the Earth, it's 80 milliwatts per square meter. So if you take solid ice as the material, then that means there's a subsurface gradient of about 1 Kelvin per kilometer. But really, I don't think that's a great number to work with, in the sense that Titan is just as complicated as the Earth. I mean, you can have There may be areas like the dunes where you've got dry sediments which have a low conductivity and the gradient will be higher. But near the lakes, there's probably hydrothermal circulation underneath and the gradients will be much lower. So, pick a number. One at the back.
Does Titan have any kind of a magnetic field?
Great question. We know it doesn't have a big one. In fact, even Voyager was able to place an upper limit on an intrinsic field. That isn't to say it doesn't have an iron core. It almost certainly has a rock core and is partially differentiated. The gravity information maybe suggests it hasn't completely differentiated. Of interest in this connection is induced fields, which are what have told us, for example, that Europa has a liquid water layer. As the applied field from the parent planet varies, you get an induced field. You get eddy currents induced in a conductive medium, like a liquid water interior. On Titan, it's been very challenging to detect those induced fields for a couple of reasons. One, Saturn's magnetic field isn't as strongly inclined as Jupiter's, so the modulation is much weaker. And second, Titan's got this thick atmosphere, which has an ionosphere. So there are currents flowing around in the ionosphere that you have to sort of subtract out to look for any induced signal. Now, Cassini actually just a few weeks ago made a special, deeper than ever dip into Titan's atmosphere during a flyby. Flew past at 880 kilometers instead of the usual 1,000 to get beneath the peak in the ionosphere. It probably looks a bit grimy after that encounter, but there was an awful lot of analysis went into making sure it would be safe. I don't know if that encounter has revealed an indication of an induced field or not, but that's what we'd look for. Ideally, on a future mission, you'd have an orbiter to measure the applied field and a lander to measure the induced field. You can separate out the variables, but it's quite a challenge with Cassini. But we know there's not a large residual or dynamo field.
We don't have any further questions. Ralph, we have a special SETI pin.
Awesome.
That
Thank you.
hopefully will guide you through your future studies from Titan.
All right.
Join me in
Look forward to
thanking
wearing it.
Ralph.
Thank you.